Hi, I am Mrs. Shea. Today I am going to talk about sequences in algebra. In this video, I am going to introduce two common data patterns, geometric and arithmetic sequences. By learning the characteristics of the sequences of the data, you will be able to identify what are geometric and arithmetic sequences. Of course, there are other types of special series too, which you can explore at the end of the video. Understanding how to sum the sequence of data and how to find the mean of the data are important in data analysis field. Today, I am going to show you how to use recursive and explicit formula to calculate the nth item of the sequence and the total sum of n items. A set is a well-defined unordered of distinct elements. When a set has a specific pattern or order, it can be further described as a sequence. Being able to recognize the pattern in numbers is helpful. People in areas such as cryptology, finance and signal processing study these types of sets all the time to predict changes over time. For example, the sequence of ordered regular polygons, the sequence of powers of 2, the sequenae of ordered square numbers. We will study the two most common types of sequences. First, let's take a look at the arithmetic sequence. In an arithmetic sequence, the numbers have a pattern. The numbers adjacent to each other have a common difference, for example, 3, 5, 7, 9, 11, 13 and etc. There is a pattern in these numbers. The same common difference 2 is added to get to the next number. Similarly, the same common difference -1 is added to get to the next number in the arithmetic sequence 6, 5, 4, 3, 2, 1. The set of a sub 1, a sub 2, a sub 3, a sub 4 etc. is written with curly bracket 1, 3, 5, 7. Second, let's take a look at the geometric sequence. In geometric sequence, the numbers have a pattern too. The same common ratio r is multiplied to get to the next number. For example, 3, 6, 12, 24, 48 and etc. This is a geometric sequence with ratio r equals 2. Similarly, the sequence 48, 24, 12, 6 is a geometric sequence because first number is multiplied by constant ratio 0.5 to get to the next number and same pattern continues to the rest of elements in the sequence. Another example of geometric sequence set of b sub 1, b sub 2, b sub 3 and b sub 4 is written as curly bracket 2, 4, 6, 8, 10, etc. The nth term a sub n is equal to 2n. Let's do a practice. As you have just learned in previous slides, when the adjacent data has a common difference, the sequence is an arithmetic sequence. Since the number after 2 is 5, the difference is 3, the next adjacent number after 5 is 9, but it has a difference of 4, which shows the sequence doesn't have common difference number. So the first sequence data is not arithmetic sequence. The next set of data 2, 9, 16, 23, 30 and so on is an arithmetic sequence because the adjacent data has a common difference of +7. When the adjacent data has a common ratio, the sequence is a geometric sequence. In the third data set, the number after 3 is 15, the ratio between adjacent data is 5, and that ratio is the same for the next adjacent data and so on, therefore, the set is a geometric sequence. We have learned the sequence and how to identify its type, such as arithmetic or geometric. Now, let's look at 3 different ways to represent a sequence. Set notation, function and table. We have learned the sequence and how to identify its type, such as arithmetic or geometric. Now let's take a look at the sum of the first n numbers in the sequence, which is called a series in mathematics. S sub n equals the sum of a sub 1 plus a sub 2 plus a sub 3 etc. till a sub n. In math, it is written using sigma notation, the sum of first n terms. The series can be infinite or finite. A series diverges if its partial sums do not approach a finite limit, meaning the sum grows towards infinity, negative infinity, or oscillates. Let's analyze the arithmetic series and identify the sum of the arithmetic sequence. The terms in this sequence have a common difference d, and we can establish the recursive formula as a_n equals a_n1 plus d. First, enumerate all the recursive formulas from a sub 1 to a sub n. Next, consolidate the left sides and the right sides of these equations. The left side sums to s sub n, while the right side equals s sub n1 plus n1 times d plus a sub 1. Subsequently, we will move s sub n1 to the left side of the equation. By definition, the difference between s sub n and s sub n1 is a sub n. This allows us to derive the explicit formula for the nth term. The sum of a sub 1 and a sub n divided by 2 provides the mean value of the sequence. Importantly, we will express the summation in both forward and reverse order, utilizing the nth term formula from a sub 1 to a sub n and from a sub n to a sub 1. Upon adding the left and right sides of these summation equations, we eliminate the common difference d, which leads us to assert that 2s sub n equals n times the sum of a sub 1 and a sub n. In this example, you will use the formula to calculate nth term. First, identify what type of sequence it is: -7, -3, 15.9 and so on. By finding the adjacent terms, you shall know the adjacent terms have common difference of 4, so this is an arithmetic sequence. Next, calculate d based on the adjacent terms, d equals 4. Last, use the explicit formula to get the value of 40th term. A of 40 is equal to 149. Next, in the example, we need to use the series formula to get the sum of 50 terms starting from 4 to 50th term. First, identify the sequence type. By looking at the adjacent terms, we can determine it is the arithmetic sequence. Since you have learned in previous slides that series formula uses the first and 50th term, let's calculate 50th term of this sequence first using explicit formula, then find the sum of 50 terms using series formula. Finally, you get s of 50 as 6325. In geometric sequences, the formula is represented using the ratio r. There are also recursive and explicit formulas. You can easily derive the explicit formula using the substitution method. Lastly, to find the sum of all the data for a geometric sequence, you can derive or memorize the formula. S of n is equal to the difference of 1 minus r to the nth power divided by the difference of 1 minus r. In this example, the sequence of data has a pattern of -2, 6, -18, 54, -162. First, we look at the pattern in data, and since the first term and the second term have a ratio of -3, and the same ratio holds for all subsequent adjacent terms, we know it is a geometric sequence. Use the explicit formula when the question is to find the nth term and the terms are far apart. By plugging into the initial data value, ratio and exponent number, we can conclude the answer is 39,366. Let's work on this example. Find the sum of the first 11 terms of the following sequence: -256, 128, -64, 32, -16 and so on. By looking at the sequence, it can be identified as a geometric sequence with ratio -1/2. Plug in the series formula in the previous slide, you can conclude the sum s of first 11 terms are 170.75. Here is the summary of all the formulas that I have done so far in the video. You can practice the questions. The first question is arithmetic sequence, the second question is geometric sequence. Practice more to get yourself comfortable with using the formula of geometric and arithmetic sequences. In this slide, I would like to introduce a concept, limit. You will learn limit in pre-calculus or calculus courses later. However, since you have known series, and series is the sum of the numbers in ordered set, Understanding there can be infinite numbers in the ordered set, for example, an infinite geometric series will have infinite numbers and they go on forever. Does it converge? Let's take a special case where absolute value of ratio r is less than 1 and larger than 0. So according to the series formula, you probably can find that the term r to the nth power shrinks as n gets larger, which lead to the term approaching 0 as n is getting larger. That tells us s approaches a limit of 1 times the reciprocal of 1r. In this slide, I introduce two types of mean. The first is the arithmetic mean. It is the average value of the n items. The second is the geometric mean. It is the nth root of the product of n values. This slide gives some common formulas for several sequences. Remembering those can be helpful when you learn high-level math in college. Lastly, I would like you to take a look at the famous Fibonacci sequence. It is a series where each number is the sum of the two preceding ones. For example, given the first is 0 and 1, the next is 1, 2, 3, 5, 8, 13 and so on. This sequence can lead to the golden ratio 1.618 and has amazing applications in nature. As the sequence progresses, the ratio of a number to its predecessor approaches this divine proportion, which is called the golden ratio. The triangular sequence has a link to a video if you would like to explore. Thank you for watching my video. See you next time.